On July 1, 2025, beneath the clear, star-studded skies of Chile, the Atlas Survey Telescope made a remarkable discovery. Astronomers noticed a faint, fast-moving point of light, an object tracing a hyperbolic path across the heavens. Its trajectory was unmistakable. This was no ordinary asteroid or comet but a true interstellar traveler, a visitor from far beyond the boundaries of our solar system. The object was soon named 3-1 Atlas, marking it as only the third interstellar object ever detected passing through our cosmic neighborhood. Each of these rare discoveries is a milestone in astronomy, opening a fleeting window into the mysteries of the wider galaxy. Interstellar objects are like messages in bottles cast adrift from distant worlds. They are rare, precious samples, fragments of other planetary systems that have journeyed for millions, perhaps billions of years before reaching us. Each one carries clues about the chemistry and history of places we may never visit. Their arrival offers scientists a unique and extraordinary opportunity, the chance to study the building blocks of alien worlds without ever leaving Earth. By analyzing their composition, astronomers can piece together stories of cosmic formation and evolution, gaining insights into how planets and solar systems are born. The discovery of 3Y Atlas sent a wave of excitement through the global astronomy community. Teams around the world mobilized instantly, racing to observe the object with every major telescope at their disposal. They knew the window to study this interstellar visitor would be brief, and every moment counted. Even from a great distance, 3I Atlas was already showing signs of activity. It began emitting gas and dust as it passed beyond Jupiter's orbit, a behavior that hinted at the presence of exotic, highly volatile materials, substances that may be rare or even unknown in our own solar system. This early and unexpected activity marked 3-1 Atlas as something truly different, a cosmic enigma, brimming with secrets from the depths of interstellar space. For astronomers, it was a tantalizing promise, a chance to unlock new knowledge about the universe, and perhaps about our own origins. To grasp 3I Atlas's significance, we look to its predecessors. In 2017, Oumuamua arrived, small, tumbling, and mysterious, with no tail but a puzzling acceleration, sparking wild theories. 2 years later, Borisov appeared, a classic comet with a familiar composition, confirming that other star systems can make comets much like ours. 3I Atlas, however, was neither a stealthy enigma nor a familiar cousin. It combined interstellar speed with a bizarre chemistry and structure defying easy classification. Its intense early activity suggested it was made of far more volatile material than any local comet. These three visitors, Oumuamua the mystery, Borisov the cousin, and Atlas the wild card, showcased the galaxy's diversity. But Atlas, as we'd soon learn, would teach us about hidden dangers when a fragile visitor meets the sun. In 2025, astronomers had powerful new tools, quantum-inspired algorithms and atom interferometers, to analyze 3Y Atlas in real time. These technologies rapidly processed telescope data, revealing the comet's trajectory, chemistry, and structure in hours, not weeks. The algorithms flagged Atlas's bizarre chemistry almost immediately. Atom interferometers precisely measured its mass and density, adding crucial details to the puzzle. This leap in technology transformed planetary science, letting us understand and predict the behavior of cosmic wildcards almost instantly. Rapid analysis wasn't just about curiosity, it was about planetary defense. Interstellar objects arrive unannounced with unpredictable properties and speeds. The ability to quickly characterize such threats is now essential. Atlas was a test of our readiness for the unknown. The data painted a portrait of a truly bizarre object, unlike anything astronomers had seen before. As scientists pored over the numbers and images, it became clear that this was no ordinary visitor from the depths of space. 3I Atlas raced through the solar system at a breathtaking 61 kilometers per second, over 136,000 miles per hour. At such incredible speeds, it was moving fast enough to cross the distance from Earth to the Moon in just over an hour. This velocity made it one of the swiftest objects ever observed in our cosmic neighborhood. Its chemistry was shocking, an extreme carbon dioxide to water ratio of 8:1, far higher than any known comet. Most comets are dominated by water ice, but Atlas was a true outlier, with carbon dioxide making up the vast majority of its volatile materials. This suggested it formed in a very different environment, perhaps in a region of the solar system rich in carbon dioxide or altered by unique cosmic radiation. Its birthplace may have been far from the sun, in the cold, shadowy outskirts where such chemistry could persist. The high CO2 content explained its early activity. Carbon dioxide sublimates at much lower temperatures than water ice. Even when still distant from the sun, Atlas began to release gas, creating a glowing coma and a faint tail long before most comets would stir. As Atlas neared the sun, it fizzed away like a giant block of dry ice, its coma and tail growing rapidly. The closer it got, the more dramatic its transformation became, as sunlight unleashed torrents of gas and dust from its fragile surface. Its density was extremely low, less than half that of water, making it more like a cosmic snowball than a solid rock. The nucleus was likely a loose, porous collection of ice and dust, held together only weakly by gravity. This combination of speed, volatility, and fragility set the stage for a dramatic encounter. Atlas was not built to last, it was a fleeting visitor, destined for a spectacular fate as it raced toward the inner solar system. Atlas was a delicate wanderer, ill-equipped for the sun's harsh welcome. Its journey would be brief, but its story would offer scientists a rare glimpse into the strange and beautiful diversity of our solar system's icy wanderers. Atlas's timing was dramatic. It arrived during the peak of solar cycle 25 when the sun was at its most violent. Solar flares and coronal mass ejections filled space with charged particles and intense radiation. For a fragile, volatile object like Atlas, this was a perfect storm. The solar wind and radiation would heat its ices explosively, creating jets of gas that could tear it apart. Simulations showed Atlas was likely to fragment. Its loose, porous structure couldn't withstand the sun's fury. The question wasn't if it would break up, but when and how violently. Unlike seasoned local comets, Atlas was a pristine relic, unprepared for such extremes. Its journey became a live experiment in cometary destruction. We were witnessing what happens when a delicate interstellar snowflake meets a raging star. The breakup of Atlas wasn't just a spectacle. It posed a real and immediate threat to our planet and the technology we rely on every day. When a comet like Atlas shatters, it doesn't simply vanish into the void. Instead, it leaves behind a chaotic trail of debris, each fragment hurtling through space at incredible speeds. As these fragments spread out along the comet's original path, they form what's known as a meteoroid stream, a vast, invisible river of rock and ice particles. If Earth's orbit happens to intersect this stream, the consequences could be dramatic and far-reaching. We wouldn't just witness a beautiful meteor shower. Instead, we'd be bombarded by fragments moving at over 60 kilometers per second, far faster than a bullet, and with much more destructive potential. The sky could light up with streaks of fire, but the danger wouldn't end there. At such extreme velocities, even the tiniest grains of dust could punch holes in satellites, damage sensitive instruments, or even trigger a catastrophic chain reaction of collisions in Earth's crowded orbital highways. Our global communications, navigation, and weather monitoring systems could be crippled in moments. On the ground, the threat is just as real. A dense stream of meteoroids could ionize the upper atmosphere, creating plasma that disrupts radio signals, GPS, and even power grids. The resulting geomagnetic storms could plunge cities into darkness and sever our links to the outside world. Our current planetary defenses are built to detect and deflect large, singular asteroids, not sudden, unpredictable clouds of high-speed debris. This kind of threat exposes a critical gap in our preparedness. The sudden and unpredictable nature of Atlas's breakup meant there was little time to react, let alone mount any meaningful mitigation efforts. Scientists could only watch as the situation unfolded, powerless to intervene. Some of the most alarming risk assessments were kept classified, shared only among top government officials and space agencies. This secrecy underscored just how serious and unprecedented the threat truly was. The Atlas event forced humanity to confront a new kind of celestial hazard, one that is diffuse, fast-moving, and potentially overwhelming. It was a stark reminder that space is not as empty or as predictable as we once believed. As Atlas swung past the sun and vanished into the dark, it left us with data and questions. Did it survive or did it shatter into a cloud of debris? Probes like Juno will help us find out. Its origins remain a mystery. Tracing its path back to a parent star is nearly impossible. Atlas is a message in a bottle, but the sender's address is lost to time. This encounter highlighted the unpredictable nature of interstellar threats. Faster, stranger, and more fragile than anything we've prepared for. It underscored the need for rapid detection and analysis technologies. Atlas expanded our understanding and revealed our vulnerabilities, but also our growing ability to respond. Its fleeting visit will have a lasting legacy, pushing us to prepare for whatever the cosmos sends next.